Okay, we're up to part 18 in the RevSim Virtual Coffee Break Series, short webinar series. And in just a minute, Alan Chalker of the Ohio Supercomputer Center is going to talk to you about a valve design case study. Just keep in mind, these are intended to be in 10 minutes or less, just a quick walkthrough of a case study. And to get more information on this or any that you've seen, you'll generally find the link at the end of the case study to where you can get more detail. You can always get that through RevSim.org, and typically you can get it from Alan or Wolfgang themselves. Just quickly about RevSim, if you've not yet gone, I invite you to take a quick tour of the site. In addition to these webinars, you'll find some other topics that are covered. You'll find just a host of resources, including papers, presentations, videos, and so forth. You'll also see there where you can sign up for our newsletter. And in addition, I invite you to follow us on LinkedIn. You'll get a weekly update, just some of the things that are coming up industry-wide, not only regarding RevSim, but just the simulation community as a whole. Quickly, I invite you to become one of the stakeholders. And if you notice on the site, you'll see a link where you can contact us. I invite you to contact me, Bob Farrell, and I can talk to you a little bit more about where you might fit in. In addition to getting information from the site, we encourage you to help participate by suggesting content and even providing content yourselves. And again, that's something I'm happy to talk to you about. So again, I'm going to turn things over to Alan now, and he's going to take you through the case study.
Okay, thanks, Bob. So in this virtual coffee break, I'm going to talk about valves. And as you can see here in this slide, there are a variety of kind of micro valves that are made by a company based in Cincinnati called Clippard. These are used for everything from medical devices to industrial devices. They're generally all pneumatic, and the idea behind them is that they're going to take a electrical signal to feed a solenoid. That's why most of them have some sort of kind of cylindrical component to it. Feed a solenoid that pushes a plunger up or down, that then open or closes or kind of pinches or blocks an outlet or an opening to allow or prevent air from flowing through, in this case, pneumatics, so it's pressurized air. So Clippard has been around for quite a while, and they've been doing a variety of things in the past in-house with modeling and simulation, but they were having a particular problem with a proportional valve. So a proportional valve means that it's not just open or closed. It actually is partially open or partially closed depending upon the amount of voltage or current really that's being fed into the solenoid. So they partnered with our awesome program, which is our industrial outreach program at OSC, and we brought in a local expert service provider that has some expertise in moving parts and finite element analysis and things like this. Now, the thing about a nonlinear, or the thing about a proportional valve is that it's nonlinear. The way that it controls that partial opening or closing is that the solenoid is pushing against some sort of spring. And they were not getting consistent flow in terms of the amount of current that they expected to put in based upon the design specs versus how open or closed that was. Now, when I said spring, most likely you thought of a traditional wire-wound coiled spring. But in the case of the Clippard design, the spring looks more like a washer. It's kind of a flat spring thing that this is looking down on top of it, but if you looked at a cross profile of it, you would see that this is actually kind of higher in the center than it is on the outer edge. This particular spring that they had in here was being machined, and you can imagine the processes involved in machining such a thing. And they were pretty sure that there was something wrong with the fact that spring, as it was being machined, was not aligning with the actual specs that they expected it to have. So the thing that's unique about this case study is that it is not entirely virtual. What we did is we worked with this engineering service provider, Kinetic Vision, that has access to a CAT scan, a CT scanner for industrial components. So they put the entire valve in the CT scan, got a whole bunch of data off of it, and as a result of that, we then took that data, processed it to create a 3D model of this valve as it was working, and they very quickly discovered that there was an issue with the manufacturing process of that particular spring, in that it wasn't the thickness they thought it was. And so what you're seeing here in this visualization is a profile of the relative thickness of the spring at different areas. And you see some areas are blue, some areas are yellow. So it's giving you inconsistent thickness, not within the spec that they thought that it was going to be. As a result of that, they knew that they had a manufacturing process, not a design and simulation issue. So they were able to go back to the manufacturing process and tighten up the tolerances there to get this particular component to match what they actually were speccing. And as a result of that, it then matched the models and the simulations, and they were getting the expected nonlinear performance of this valve. So if you want to know more about this one or really any of our case studies, we publish all of them on our website. You're welcome to go there, osc.edu, sign up to contact us. Wolfgang also publishes all of his case studies that he's been covering in this series on his website at the Uber Cloud. And I want to reiterate what Bob said at the start, that we really do want you to participate in the website, the revolutioninsimulation.org or RevSim. You can register there. It doesn't matter what role you have. There's a role for you in the website. And so with that, on behalf of Bob, Wolfgang, and myself, Alan, thank you so much for listening, and stay tuned for our next virtual coffee break.